Now we want to show how consistency models work, especially sequential consistency. As we have seen, coherence means that writes to a single location are visible to all processors in the same order, and consistency means that writes to multiple locations are visible to all processors in an order that makes sense. Peterson's algorithm writes to the variables turn and interested, and these writes need to be seen in order. If writes to all locations need to be seen by all processors in the same order, then we have sequential consistency, abbreviated SC. What would we expect this code sequence to print? Well, P1 sets A to 1 and then sets flag to 1. P2 waits for flag to change value, then prints A. So we'd expect the code sequence to print 1. And with sequential consistency, we know that it would print 1. With another consistency model, it might not. The writes to A and flag might be seen in a different order by P2 than by P1. Coherence is no help in this situation. It only keeps writes to a single location in order. It doesn't have anything to say about the ordering of writes to two different variables. Take a look at another example. P1 executes A equal 1, B equal 2, and P2 executes print B, print A. What will be printed if the statements are executed in the order 1A, 1B, 2A, 2B? And what will be printed in these other cases? These three execution sequences exhibit sequential consistency. They are in accord with what the programmer would expect. But is it possible for A to be printed as 0 and B to print as 2? Yes, but only if P2 sees the two writes by P1 out of order. This could happen if the compiler or interconnection network reorders them. This shows why we need a consistency model to constrain what happens to different locations, as well as needing cache coherence. A memory consistency model can be considered to be a contract between the programmer and the architecture. Some of the responsibility for keeping writes in order lies with the programmer, and some lies with the architecture. It specifies the order in which memory operations, which take place in order at the processors where they occur, can appear to execute throughout the rest of the system. Programmers need to know what the architecture guarantees so that they can program appropriately. For example, they can't use Peterson's algorithm on a system that's not sequentially consistent. Compiler writers need to know which consistency model is in use because the model will likely require that certain memory operations be compiled into the machine code in the same order that they occur in the source code. Architects need to understand the model too because, for example, write buffers might need to be flushed to memory in FIFO order. Now we turn our attention to the most intuitive consistency model, sequential consistency. Leslie Lamport is probably best known as the originator of LaTeX, but he won the Turing Award in 2013 for contributions to the theory of parallel computing. One of these was sequential consistency, which he defined in 1979. A system is sequentially consistent if it always produces a result that is the same as if all the processors in the system executed their operations in some order, and each processor sees the same ordering for these operations. Of course, this implies that memory operations are visible to all processors. In other words, that there is a global memory and no private caches. The ordering of operations is achieved by interleaving the accesses made by different processors. As shown in the diagram, it's as if the system randomly chooses which process to take its next access from to create a total order. The individual processors, meanwhile, perform their memory accesses in program order, and the memory accesses take place atomically. In other words, no other memory operation is in progress while a processor is accessing memory. Program order is the order that instructions appear in the source code. The compiler isn't allowed to reorder operations to shared variables, though it can reorder memory operations to private variables. This prevents some optimizations and is one reason that parallel programs are inherently less efficient than serial programs. It's sometimes possible, though, to attain a sequentially consistent result, even if the execution sequence is not sequentially consistent. Here we see again our system of two processes, one of which assigns new values to A and B, and the other of which prints B and A. As we saw earlier, the outcomes 0, 0, 1, 0, and 1, 2 are all possible for A and B under sequential consistency, but 0, 2 is not. It's not hard to prove that 0, 2 is impossible. By program order, we know that 1A precedes 1B and 2A precedes 2B. A equals 0 implies 2B precedes 1A, and by transitivity, this implies 2A precedes 1B. But B equal 2 implies 1B precedes 2A, which leads to a contradiction. But it's possible for a non-sequentially consistent sequence to produce a sequentially consistent result. 1B precedes 1A, precedes 2B, precedes 2A, produces the result 1, 2 equals AB, which is a sequentially consistent result despite executing out of program order. Of course, not all executions out of program order produce sequentially consistent results, as we saw with the ordering 1B precedes 2A, precedes 2B, precedes 1A. So sequential consistency doesn't prohibit all reorderings. It's just tough to figure out which reorderings can be allowed. Because sequential consistency requires a single ordering of all memory operations in all processes which appear in program order, two conditions are necessary. First, the operations of one process become visible in program order, and all other processes see them in the same order. Second, memory operations are atomic. They don't overlap, and all processes see them in the same order. Atomic writes are easy if there's a shared bus. Without a shared bus, making writes atomic is hard. It's no problem for reads to be atomic because a read is finished when the data returns. But a write is harder. How can every processor in the system know that a write is done? Clearly, we can't afford to send a message to each processor every time a write completes anywhere in the system. And as we have seen, enforcing sequential consistency requires a partnership between the compiler and the architecture. The compiler has to compile most instructions in order. The architecture has to assure that writes go to memory in order. And what's even harder, it has to make them atomic. Write atomicity means that the same write ordering is seen everywhere, just as if the writes all had to go across a shared bus. In this three-process system, P1 sets A to 1, P2 waits till A changes in value and then sets B to 1, and P3 waits till B changes value, then prints A. In a sequentially consistent system, A would print as 1, but in a non-SC system, it might not. There is a problem if P2 leaves the loop, writes B, and then P3 sees the new B but the old A. What about our write-through protocol? Is that SC? We will assume that there are no write buffers and that loads and stores in every process complete in program order. Yes, it is SC. The atomic bus solves all the problems. It serializes all writes and all read misses. A read always returns the value from the most recent write. All writes go to memory, and any subsequent read will read the value that has just been written. Since all writes go across the bus, no processor can see a write. That's what it means when it says a write completes with respect to a processor. Unless all previous writes have finished going across the bus. Thus, a global ordering of writes is assured. So in summary, one solution viable for small-scale multiprocessors is to use a shared bus. State transition diagrams can be used to show how a cache coherence protocol operates. The two main types of coherence protocols are invalidate and update. Sequential consistency guarantees that memory operations are seen in order throughout the system.